Hi.
Recording in.
Hello, thank you for joining us. So Mike, I am Mukhammadali. So today I'm going to be hosting this interview, this amazing interview with you. We really appreciate your joining us and your commitment and your time. And just to remind, this is going to be our first interview in our Falak interview series. And for all our viewers, today we're going to have an interview on the topic of James Webb, the contributions and achievements of James Webb telescope, and its contribution to the fundamental physics and astronomy. Our guest today is going to be Mike Boylan-Kolchin, an associate professor from the University of Texas at Dallas. Is going to give us a presentation about the telescope and its accomplishments, and as well as the future contributions of the telescope. Mike?
Thank you very much. It's really an honor to be here and to be able to talk with you about this. And I hope that if you have questions as I'm going through this, that you'll feel free to let me know, because this is a very exciting subject and also a very confusing one, even.
Sure, of course. Hello?
I'm sorry, I don't know what happened there. Can you hear me?
I'm sure, yeah, everything's okay.
Yeah, I'm sorry, I don't know what happened. That was very strange. I'll just try to keep going. I'm sorry. What I was saying is that I think this is a very exciting time for all of us working in this field, a very exciting and confusing time, and I'll try to convey some of that, both the excitement and the confusion that are happening here. So I think the starting point is we have this picture for our understanding of the universe. It starts about 13.8 billion years ago in an era of quantum fluctuations and ends so far in, yes?
Sorry. Sorry. Sorry.
Oh, no problem. And I think the end of this this era of investigations today is at this dark energy era where we have accelerated expansion of the universe. So in between, there's some pretty amazing things that happen. So just as a reminder of the sort of amazing nature of our universe, it's very improbable how our universe looks, and actually pretty incredible. So it's over 45 billion light years in radius. That's just the observable universe, though. The entire universe might actually be infinite in extent. The universe, we think, is 13.8 billion years old with a very, very small uncertainty, so only 23 million years. And all of the cosmic structure we see around us came from quantum fluctuations in the first fraction of a fraction of a fraction of a second into the universe's existence. Maybe what's even more amazing is that the building blocks of everything that we know, the protons, electrons, neutrons, all of that that's around us, account for only about 5% of the matter and energy we see in our universe. The rest is so-called dark matter and dark energy that we only see through its effects on the clustering of matter in the case of dark matter, or through the expansion of the universe in the case of dark energy. And not only is the universe expanding, which was an amazing discovery in and of itself, we've also discovered that that expansion is accelerating. And this is totally unexpected in our basic models of the universe. We always think of gravity as being attractive. And so therefore, as the universe expands, gravity should make it slow down, should slow down that expansion. So there's a lot of exciting stuff that we already have discovered about the universe, but we know very little about many of these things. So some of what I'd like to talk about is how did we get this knowledge, and where is the space for the new discoveries? And I think James Webb comes in very well there. So as I mentioned, if you sort of do a budget, a pie chart of what the universe contains today, there's a few different things. There's this atoms, the regular matter that we can think of. There's dark matter, which accounts for something like 27%. And there's dark energy that accounts for much more, almost 70% today. So the matter that we know, the normal matter, only accounts for something like 5% of the matter and energy in the universe that we know of. But that's just today. If we go back in time and look at earlier times, we can understand some different things. And in that case, what we see is a very different picture. So this is the place where we can measure the evolution of the universe the best. This is the baby picture of the universe, the cosmic microwave background. And it's a picture of slight temperature variations across the sky in photons we're receiving today that are left over from the Big Bang. So the typical photon temperature here is 2.7 degrees Kelvin. And the difference from the hot spots, the red, to the cold spots, the blue, is only of order microkelvin. So maybe 10 or 20 microkelvin, tiny, tiny difference from point to point in the sky. And so this tells us that the universe was a very smooth and homogeneous place at very early times. This light comes to us from about 380,000 years after the Big Bang, when the universe was 1,000 times smaller than it is today. And it turns out that the origin of these hot and cold spots is actually sound waves traveling at 60% of the speed of light in the early universe. So the early universe was very hot and dense. There was a lot of energy in the photons and the electromagnetic radiation that was very tightly coupled to the electrons and to the regular matter in the universe. And so what happened is, if there are little overdensities, the gravity pulls it in, but photons feel pressure. And so eventually it wants to push back out. And this whole fluid oscillates with a certain sound speed. That sound speed is 60% of the speed of light. So these sound waves are matter and radiation squeezing into and expanding out of dark matter overdensities that are only about a part in 10,000. So the whole universe was very smooth, with differences in density from point to point that were only about a part in 10,000 then. And we've learned from this that the universe hasn't always looked the way it did. If you look at the pie chart at earlier times versus today, remember today what we have is 5% of the matter is in radiation, is in atoms and normal matter. If we look at earlier times, though, we find something very different. We find that the normal matter is much more. Atoms are actually 12%. We see that the photons, the light and neutrinos, light particles, were 10%, and dark matter was actually 63%. So most of the universe's energy density was actually in dark matter at that very early time back here. Okay, so that's a very different universe than our universe today. So the big picture here is the universe has been expanding and cooling since the Big Bang. Matter and energy from in the universe get diluted because of this expansion, and the universe is also clumping over time. So since 50,000 years after the Big Bang, because of this gravity. So I thought I'd show, sorry, I have to do one thing quickly, then share again here, sorry. Okay. This is a movie of the way structure forms in the universe, we think. So on the left, you see dark matter at early times. It's very diffuse, but as time goes on, you see it clumping up more and more. Okay. And on the right, what you see is the gas temperature. And so the distribution of the gas follows the distribution of the dark matter because what we see is that the gas falls into the gravitational potential wells that the dark matter provides. So dark matter is really the glue that is holding everything together, and it's telling the matter in the universe where to collect up and form regular structures that we see today. Okay, so what does that tell us about the evolution of the universe? Even though we've only made it about 4 billion years into the evolution of the universe here, I might stop now and we can move on to the next one. So some of the big questions that this asks are, what is dark matter? What is it, which is causing all the matter to clump up in the universe? What is dark energy, which is causing the universe to accelerate in its expansion? How fast is the universe expanding today? And when did the first stars and galaxies form, and what did they look like? And again, the sort of point of this talk is that the James Webb Space Telescope should tell us about all of these things. The first three we might think of, well, the first two certainly is fundamental physics, the nature of dark matter, the nature of dark energy. The third could be fundamental physics. It could be something more about astrophysics or cosmology. And the fourth is a nice combination of all of these, I think, about when the stars and galaxies form and what do they look like. So just as a brief introduction, the way we actually observe distances in the universe and things that are far away is not by measuring the distance directly. What we measure is the redshift of light. So we know the spectrum of light in the universe from certain elements, let's say hydrogen. And if we know what hydrogen looks like in the universe, then we can, we can understand the distribution of that hydrogen, and we can, we know what the very specific transitions that hydrogen has in terms of wavelength should be. So for example, if we want to understand light that's coming from standard transitions of atomic hydrogen, we would say see a line at 912 nanometers that would correspond to the Lyman alpha transition, or sorry, 1216 angstroms, and that could correspond to the Lyman alpha transition. And if we see that, but at a different wavelength, we know that that light has been stretched out as it's been moving between us and the light when it was emitted. And that stretching is due to the expansion of the universe. And we talk about that in terms of this redshift. So just how much has the light been stretched out relative to the time when it was emitted. And so, for example, this light was emitted at very early time, it's stretched out, and this redshift factor just tells you the wavelength we observe it at relative to the wavelength it was emitted at. So this is a direct measure of how big the universe was at that time relative to how big it is today. So in this example, we see that the light has been stretched out by a factor of 3. And so that means the redshift, this factor Z, is 2. It means the light came from us to us from when the universe was a third of its current size. Here's at redshift 1 when the universe is half of its current size, and here's today when the redshift is its present size. If we want to see very early things, what we need to see is light from hot and young stars, which is emitted in the ultraviolet in the rest frame, but we need to be able to see that here on Earth. And so as that light travels, it gets stretched out from the ultraviolet into the visible, and then past the visible into the infrared. And so Hubble Space Telescope is an optical and ultraviolet and very near infrared space telescope. So it was very good at seeing light that was stretched out a bit, okay? But what we want to see is light that was stretched out a lot, because the universe was much smaller back then and it's had a lot of time to expand since the first galaxies formed. So James Webb Space Telescope has a much bigger coverage in this infrared, so longer wavelengths of light where light has been stretched out more substantially. And what this allows us to do is to push back to see galaxies that were formed earlier and earlier in the universe. So this is from the point of view of galaxies and cosmology. It also allows us to do lots of things like seeing gas and dust in galaxies that are very nearby. It has a lot of implications for planets and other things like that, but I won't really try to cover that here at all. So how does this relate to some of these questions? How fast is the universe expanding today? Well, you may have heard that we can do measurements of how fast the universe is expanding at this very earliest baby picture of the universe at this time of the microwave background. And we can do measurements of how it's expanding today. And if you look at this curve and connect it up with our best cosmological model, it looks very good on a plot like this. But on a plot like this, it's easy to hide things because there's so many orders of magnitude on the y-axis. This is the expansion rate of the universe versus the size of the universe relative to today. So if I zoom in just at the very end here, what you see is things look pretty good, except there's a little bit of a difference today. The measurement that we have in the very nearby universe from measuring the expansion directly is a little bit different than the measurement we have from extrapolating based on properties of the earliest light in the universe. So this is called the Hubble tension. And the idea is if we compute the present day expansion rate in certain units, it comes out with a number of 67. Whereas if we measure it, it comes out with a number of around 73. And so this is a discrepancy in either the model that we have for the expansion or somewhere in the data. But I think people have looked very hard to find where this issue could be in the data, and they haven't seen it. And so maybe this is telling us something fundamentally is different about the cosmological model, maybe about the nature of dark matter and dark energy than what we understood before. So one way to do this is to change dark energy a little bit to explain this. So normally in that pie chart, we had that regular matter and dark matter were about the same as photons and neutrinos at around a redshift of 3,000, so 50,000 years after the Big Bang. If you add a little bit of dark energy at earlier times, that actually changes the expansion history of the universe and changes what we infer for the properties of dark matter, dark energy, and the how fast the universe should be expanding today. So this explanation might actually tell us something about what's going on in the universe, and that there's extra interesting things happening with the dark energy sector of the universe. One side effect of this would be very interesting. It would mean the universe is actually 1 billion years younger than what we think in today. So the universe we think is 13.8 billion years. If this is really the correct explanation, that there's a little bit of early dark energy, then that would mean that the universe is only about 12.8 billion years. And that would have very important consequences for our understanding of how galaxies form and the oldest things in the universe. And I'll come back to this point again in a little bit after I talk about some of the earliest galaxies that JWST is showing us. So you might ask, how will JWST help us understand these things? And I think the best way it'll help us is to really understand the stars that are used to measure the expansion rate very nearby. So to measure the expansion rate, what you need to do is be able to link up distance to a geometry. So you need to be able to know how far away things are. And to do that, we use stars that are measured to have very specific properties. And then we can understand how far away they are based on how bright they appear to us. And JWST, since it can see in the infrared, will be able to see those kinds of stars in a different way than the Hubble Space Telescope will. And it will also be able to see them much more in dusty regions and in different parts of galaxies. So it should really help us understand whether there's something wrong with the way we're measuring the Hubble expansion of the universe very nearby. And more distant parts of the universe, it's going to use this exciting technique called gravitational lensing, the bending of light due to gravity, to measure the expansion rate. And the reason for that is that if light bends and comes back to us, it takes two different paths. And the difference between those two paths depends on how fast the universe is expanding. And so James Webb Space Telescope will enable these kind of measurements as well, which is tremendously exciting for everyone, I think. So then I think what I can turn to is maybe some of the most exciting stuff that's come out of James Webb so far, and there'll be a lot more to come out on all of these fronts soon. But this is a question about the very first stars and galaxies. When do they form? What do they look like? And what are they telling us about the universe? So again, if we sort of think about this cosmic timeline with the Big Bang all the way over here on the right and us today over here on the left, there's a lot that happened in between. So the first thing that really should matter is this sort of era of galaxies and hydrogen reionization, when stars started to turn on. And this is what Webb is really going to push us back to. So Hubble has been able to see way back to maybe redshift of 10 or so, but we think that James Webb, with its infrared wavelengths, will be able to see all the way back to maybe redshift of 15 or even 20, when some of the first stars and earliest galaxies formed at maybe 200 or 300 million years after the Big Bang. And some of the first results when people started looking at this James Webb Space Telescope data is that, to their surprise, there are really galaxies everywhere. So the expectation was that the first observations will really maybe help us understand the telescope itself a little bit, and that people will maybe see some of the galaxies that have been seen out to the distance that Hubble's seen, or just a little bit beyond, but that really it would take a long time to accumulate enough data to see things that are very far away. And what happened was, within the first 2 weeks of the data coming out, there were a huge number of galaxy candidates that were quickly being discovered all the way out to redshift of 20 or so. So remember, redshift is a measure of how big the universe was relative to now. So this is when the universe was 21 times smaller than it is today. So a very different universe than what we're looking at. This is only 200 million years or even a little less after the Big Bang. And so I'm showing you an image of one of these galaxies. This is from a colleague here at University of Texas who discovered this galaxy, which they think is at a redshift of 12 or 13. And just to show you, this is very hard, right? This is not going to win any best looking galaxy competitions, but it's very impressive to be able to detect this light from billions and billions of light years away. It's very hard, and it's an amazing technological achievement. So just to give you a sense of sort of how far away these are, this is a plot that shows you how redshift is related to time since the Big Bang, how long that light has been traveling, so the look back time, and how far away these things are. So the Hubble Space Telescope was able to get us to here or so, redshift of 10, which is about 13 billion years ago, we think, or a few hundred million years after the Big Bang. And these are objects that are now 32 billion light years away from us. But these are all candidates from the James Webb Space Telescope that go from redshift 10 all the way out to maybe redshift 20 even. So we're talking, if this is correct, about pushing the time we've seen since the earliest galaxies from, say, 400 million years after the Big Bang to only 200 million years after the Big Bang, or almost all the way back to when the galaxies could have even formed at all. So this was really a big shock, I think, to everybody who was involved. And I think one of the biggest shocks to me was that people were finding galaxies This is the plot of the stellar mass of galaxy candidates as a function of the redshift. People were finding galaxy candidates with masses that are about 100 billion solar masses at sort of the highest redshifts that Hubble could have seen. So not quite the most distant galaxies, but very early. And the point is that they're very, very massive. If for comparison, I ask how big is the Milky Way today, a galaxy that's had a chance to evolve for 13.5 billion years more than these galaxies, the Milky Way isn't even this massive, and it's had this entire time to grow to what the Milky Way is today. If I asked what the Milky Way would have looked like back then, it probably would lie way down here somewhere. Okay, so this was extremely surprising. And what this means is if you look at how much mass there is in stars in any volume of the universe, sort of the density of stars versus previous measurements, the lines here are previous measurements. This is at the highest redshift, redshift 10 is shown in red, or redshift 8 in blue. And you can see this data point here is many, many orders of magnitude, thousands of times higher than the line that was expected. So there's thousands of times more stars that have already formed than the expectations we had based on our understanding of the universe from the Hubble Space Telescope. So this was a really incredible result. Why are there so many stars in these galaxies? How have they managed to form so many stars so early into the history of the universe? There's very little time to form these stars. And so one problem that I pointed out is that if you do this, there's actually more stars in this most massive system than there is material to form stars in those parts of the universe where we think they form. So even if we ask, let's take all of the atoms and gas and everything that we have that would be where these things could form and instantaneously turn it into stars, there is not enough material that is at this high a density in the early universe to be able to form these stars. So this is a very interesting issue, because what it means, if there's really more stars than there is material to form the stars in our standard cosmology, it means that either the observers are wrong about what these galaxies are, or we've just been very lucky and measured a part of the universe that's not at all like the rest of the universe, or it's telling us something about fundamental physics and cosmology, that our cosmological model might be wrong. So let me just walk through a couple of these a little bit, because they're all interesting, I think. So what would it mean for the galaxy properties to be wrong? Well, what we actually observe is the light from these galaxies in the across some portion of the electromagnetic spectrum. And to measure the stellar mass of the objects, we need to convert between this light and the mass. And this depends on a bunch of things. It depends on how the stars have formed over the history of the galaxy. It depends on how stars form as a function of mass. Do we have lots of very high mass stars and only a few very low mass stars, lots of very low mass stars, only a few high mass stars, or something in between? And people have to make assumptions about all of these things to convert from the light that you see to the mass that we want to understand. Something else is that we need to be sure we're really measuring where this galaxy is correctly. So is it really that we're detecting the emission that we think we're seeing, light from the very early universe, or are we seeing it from still much earlier in the universe, but not at as an interesting a time? So if we actually measure the distance correctly, because if the galaxy is actually a lot closer to us, that means it's not as bright as we thought it was, and then it's not as hard to understand. And finally, we don't really know exactly how the camera on James Webb Space Telescope is working out in space. And so maybe there are some calibrations that need to be updated there. The other possibility I talked about is that the observed portion of the universe is very unusual that we looked at. So if we just happen to look, so that these observations weren't done in a specific place for a specific reason. But if we just happen to get lucky and choose a very overdense part of the universe, then this might not be an issue. But we have to get something like a part of the universe that's very different than what is normal. So we expect that we'd have to survey 1,000 times more of the sky than has actually been done to see galaxies that are this unusual. So this would be a very strange occurrence. And the final possibility is that there's an issue with our cosmological model. So if we can't understand this in terms of the properties of the galaxies and the properties of the telescope, then we'll have to examine the assumptions that went into this dark matter and dark energy model. So one of the things that we could imagine is this early dark energy model that I was talking about that I talked about earlier, right? So this would allow for a more and a faster formation of early cosmological structure. And so this would be really amazing if actually this early dark energy, which was invented in some sense to try to explain this mismatch between the expansion rate of the universe and as measured at early times and as measured at late times, if that could also be the explanation for why we're seeing, we think, more structure than we expect in the universe today. But I think this really shows you how very small changes to this model can show up in a lot of places and how important it is to have astrophysical telescopes to look at these things in addition to measuring things on Earth and measuring things other ways, sort of more typical physics ways. So the other thing I thought I could talk briefly about is this question of, do we understand the telescope as well as we think? So this is an observation of something that is called a globular cluster, so a set of stars that all have the same age. And we think for globular clusters, if you plot how bright they are as a function of sort of a color, which is related to how bright they are, and the difference of how bright they are in two different bands, that these should this should just cover one sequence in this plot, okay? And what you see is this covers several sequences, and each sequence corresponds to one portion of the camera. So the camera has 8 different units. And what you can see is those 8 units aren't receiving light in the same exact way. So the camera hasn't been calibrated as well as it could be. And so what people have done is taken this initial calibration. This is where the measurements were done initially. And so, this is saying that people don't understand things very well. And they've said, well, if we apply some corrections, we can correct for that. And now we can understand the calibration. We can make this detector much better, so we can say what things really should be. And that's what's shown down here. That's what people have started to use now. So now this looks much better. All of the results lie on top of each other. And so people have started to reanalyze all of their data with this new correction for this effect of different parts of the camera seeing things in a slightly different way. And so if you do that and you go back to this previous plot that I showed, you find that some things move around a little bit, but in general, the result is still there. There's very massive galaxies at very early times. So this most massive one is about the same. The one that's at the highest redshift is a little bit less massive, but there's still just a lot more massive galaxies than we ever would have expected, even when you've updated this understanding of the camera. And so just to show you, here's an update of the plot I showed before, which asks, how do these galaxies lie in the amount of stars we have as a function of stellar mass? Previously, they were completely in this range where there's no way to form them. Now they're at the very edge of what might be possible with the universe, but this is still not at all what we expect. We don't expect everything to immediately turn into stars. And so compared to our expectations, which might be this gray or this orange line, these data points are still very discrepant. So we think that this is still potentially a big problem and might be telling us something about cosmology and fundamental physics. So how are we going to do better than this? Well, the point is there's a lot more data coming. So this is just the very first few months of operation for the James Webb Space Telescope. And so there's a lot more that's happening. Most of the data have come from 38 square arc minutes, which if I look at a point on the moon here, it's about the size of this cursor. It's tiny, tiny area of the sky, okay? And so what's going to happen is that future surveys will look much deeper, even over a wider area. So they'll be able to see even more things and see these things better, these kind of galaxy candidates better. Or they're going to see over a much wider area. So there's Cosmos Webb is going to survey even more than the area of the moon. And that will pick up these kind of galaxies as well, even though it can't see as deeply. These galaxies are so bright that that shouldn't be an issue. So I think within the next 6 months or so, we'll know much more about whether we need to really look for revisions to our cosmological paradigm or revisions to how galaxies form, or if it's more of a question of how stars are forming in the galaxies. But there's something we need to understand better, and that's a very exciting place to be. I think especially for people who are just coming into this field, it means there are lots of big questions that are left to be unanswered. And I think the very point that, you know, the telescope just turned on and one of the very first things that they saw was very unexpected, shows that there's a lot more out there to be learned from this James Webb Space Telescope. So one thing I also wanted to talk about is that we often call these galaxy candidates and not galaxies. And the reason for that is that all that's been done so far for these objects is to take pictures of them. So imaging or photometric observations, as we'd say. And what that means is we have how much light is coming from certain parts of the spectrum, but we don't have a full spectrum. We don't know at every wavelength how much light there is. And if you really want to know exactly what's going on in that galaxy, what you need to know is the light at every different wavelength. And just as a reminder, Hubble is mostly operating at the very far left of here. So it would cover up to about 1 micron, 1/1,000,000th of a meter. And the power of James Webb is that it really goes out much farther and that you can see the light that's been stretched out way into the infrared here. So as an example, this galaxy that I showed you before, what they see is the light at a few different wavelengths. And then they use that distribution of the light at those different wavelengths corresponding to each of these filters to figure out what redshift that galaxy is coming from. But there could be other things that would look like that. But if we could see the light at every wavelength, then we'd understand this much better and we'd know exactly what redshift this galaxy was at. So soon we'll be able to get spectroscopic observations with a different instrument on the James Webb Space Telescope of these same galaxies. And that will be very exciting for telling us in detail about the properties of these objects. So I'd say that it's revolutionizing our understanding of the earliest phases of galaxy formation. And before I say anything more about that, I'd say it's also true for extrasolar planets, for stars and clusters of stars, for galaxy evolution at lower redshift, for how black holes grow. But the result I focused on is this idea that there's a huge treasure trove of galaxy candidates in the early universe, very early universe. So redshift of 15 to 20, and also these very, very massive galaxies just at a little bit later in the universe's history. And so, you know, I think one thing we could imagine is that once James Webb is observing for longer, it will even see maybe some of the very first galaxies. If there are all of these galaxies that we can see already at with just a little bit of the data, once we have a lot more data, maybe we'll really be able to push to those very first galaxies and understand how they formed. And the first galaxies are exciting because they tell us about the distribution of the lumps of dark matter that they could form in. So that will tell us about the nature of dark matter as well. So by observing galaxies, we can understand dark matter. I also talked about how by observing these galaxies, we might be understanding the contributions of dark energy that's different than what we expected. So both of these are very exciting possibilities for understanding fundamental physics, so the idea of dark matter and dark energy with astrophysical observations. And I think, you know, we're basically challenging something here. There's something wrong, and that's an exciting place to be. So either we don't understand how to infer the properties of these galaxies, so there's something different about how they're forming, or there's something different about our cosmological model. And any of these is very exciting. Of course, the popular press will probably be most excited if it's something to do with dark matter or dark energy, so our cosmological model. And one possibility there is that it could be related to this mismatch in measurements of how fast the universe is expanding, this idea of the Hubble tension. So I think that this has just given us a little taste of what's happening with cosmology and astrophysics with the James Webb Space Telescope, and we've only seen a little bit of the data. So I'm very excited for the next few years for cosmology, fundamental physics, and astrophysics, because I think there's just a tremendous amount we can learn with the James Webb Space Telescope by looking farther and farther back. So I just want to take the opportunity to stop there and say thank you so much for inviting me and for listening to me today. I really appreciate you.
Thank you too for such an amazing presentation, Mike. It was really a great and really insightful presentation. Now our also viewers can understand why the buzz around this new telescope is so huge, and there was a lot of information about the telescope, and there are also some questions. If you would like to allot some time, we could ask some questions, Mike.
Sure.
Okay. The first question is that Mike, you know, I myself more of like fundamental physicist. That's why I like to ask this question first. It is that you know that there are two like theories in physics, that is quantum mechanics and GR, general relativity. So like many of the physicists, including me, also working on this, merging these two theories, and also we've got some hopes that James Webb Telescope can somehow help us out. So do you think that that James Webb Space Telescope can help us merge these two theories? And if it is possible, then what kind of information we should be looking for?
Yeah, it's a great question. I think a very exciting one. You know, I think the problem, one of the problems we have is that we just don't really see a great path forward for merging these two theories. They seem so disparate, and so either we need some kind of very amazing theoretical spark, or we need to see some observational or experimental crack that says something about one of these two theories isn't really working out, or here's some way that we need both kind of theories to explain. And I think that one reason that astronomy and cosmology has been so exciting for people who work on fundamental physics is that it does kind of combine these two, in the sense that we're sort of thinking about the quantum nature of the universe, of course, the particle distributions, where they're coming from in the early universe, but also we're thinking about that in the context of the growth and the history of the universe and all of its contents. And so that's clearly general relativity. So I think especially this idea that we might be understanding something about the dark energy, something about the expansion history of the universe with these kind of observations, I think that's one of the places that might lead to these kind of conclusions, because that's something where it really seems like, as you probably know, our first guess for what this cosmological constant, the dark energy, should be from a fundamental physics point of view is very, very different from what it actually is observed to be. And so if we can sort of get more information about this and see that there's more aspects to the dark energy, that might really point us in a direction to sort of think about this question a little bit more. You know, the other thing it could do is it could, if it really requires us understanding more structure at early times, it could tell us about the distribution of density fluctuations. And those are coming from an inflationary era, which probably needs a good quantum gravity description to be able to really understand everything very well. So maybe these sorts of topics would give us that kind of observational experimental push to then say, where can we start to look for these things? Because right now, I think a lot of people seem to feel like they're just kind of lost a little bit. We've got these two very successful theories, and how can you take two very successful but mutually contradictory theories and put them together? And the place where they're naturally together is in the cosmos, and that's, I think, why it's exciting to look there.
Oh, yeah. Yeah, thank you. And one more question about, as I said, the observations of the telescope is now like really exciting because they're challenging our understanding in both ways, you said. And hello, Mike?
Yes, sorry, here.
So about that, so the most exciting actually challenge for our understanding was about the cosmological models. It may be due to the fact that you said the observations that we are taking just because our cosmological model is not the way it should be. So like if you look at the history of science, like all the time you can just find out a theory. You've got like at the current time, you've got like a theory that is working, but at the same time, you will have another theory that can really explain the observation that you have. So do we have now some theories, some models that we're not now like considering to be the working ones, but anyway, they do explain the results that we are now receiving from the telescope? Do we have some types of such models?
Yeah, that's a great question. I think that we don't have something that looks very different from our current theories. So I'd say our current theories basically say we need dark matter and dark energy and regular matter. But one of the good things about our current theories is that to explain most of the observations, if we make a couple of assumptions, it requires very specific amounts of this dark matter and dark energy. And so I think there's one thing we can ask is that too restrictive? Do we need to, require different amounts of dark matter and dark energy? And that's kind of in the same theory, I'd say. And then we could ask something like, do we add a different kind of dark energy, which is maybe not very, doesn't make us feel very good because we're adding extra degrees of freedom to our theory, but it's not really a total change. And I think that seems possible. Right now, there's nothing else that is out there that really explains the observations, even the current observations, not let alone the new ones, on these big scales that competes with this model of dark matter and dark energy. People are trying to build modified gravity models, I would say, but it's very difficult to do detailed predictions about the cosmic microwave background at the level that we can get with the current dark matter and dark energy models. And that's not to say that the models of modified gravity have to be wrong, and I think they're very interesting to look at. But as you said, until you can sort of explain all of the existing data and the new data, you don't sort of want to maybe jump ship from one model to another model. You want to have that expanded explanatory power. And I don't know of anything that has that expanded power that's not just sort of taking our current models and modifying them a little bit. But I think the exciting thing is maybe there's something we're all missing. And like you said, trying to think about how gravity and quantum mechanics come together. Maybe there are effects we haven't considered here.
Mm-hmm. I see. Thank you, Mike. And at the end, I'd like to ask a very, maybe a humorous question to you. So it's about the James Webb telescope. So when I first saw the telescope, the first question that came to my mind is like a layman question. So how is the telescope protected from the space? Like if you look at all the before coming telescopes, they were protected from they were like seriously protected. About the James Webb telescope, we can't tell the same thing. So how's that possible? How can we rely on the data that James Webb Telescope is now sending us, considering that it is not, for example, just protected from the outer effects of the, like the stuff around it? So
yeah, it's a good question. Because I think that we sort of have models of what's floating around out there at the distance where the James Webb Space Telescope is, and it's protected from heat from the sun on one side by a full sun shield. But the other side, there's the light can come in, so other stuff can come in as well. And in fact, there have been a few impacts on the telescope itself, on the detectors, by micrometeorites, so very small particles of dust or other things in space that are in rock that are impacting the telescope. And so there were some predictions for how long it would take before that would degrade its capabilities. So far, it hasn't seemed to be too bad. There's something that hit it, a small thing, and made a little effect. That's something they can measure, but I think that maybe we learn a lot more about what's going on in the near Earth environment from these impacts than if it turns out a lot of things start to hit it. So it doesn't have any defenses that you can turn on, unfortunately, not like Star Trek or something. That would be great. But yeah, if there's a lot more stuff out there, it may hit it, and that would be terrible.
Yeah.
So fingers crossed. Yeah.
Yeah, I see. Like the best thing you can do is hope. Okay, I see, Mike.
Yes.
Thank you very much, Mike. So just to somehow summarize your words, like it looks like we're standing on a really great times, because like it is just a sign of revolution that may be coming to our understanding of the universe. So thank you very much for your joining and for such great information and explanation that you gave and your answers for the questions. Thank you very much, Mike. And if you'd like to, you could give us some concluding words.
Yeah, sure. Well, again, I want to thank you very much for the kind introduction and the kind, giving me the opportunity to talk here. And I think you're exactly right that this is a very exciting time. People often say, well, we understand so much about the universe. There's dark matter and there's dark energy. What's there for me to do in this? And I always say, look, dark matter and dark energy are just kind of placeholders. We don't understand either of them at all, I'd say. And so we're really at a place now where we can start to do that, where we can really start to ask the exciting big questions. What makes up our universe? How do we combine the biggest scales and the smallest scales? When did the very first stars in the universe form? How did the first galaxies shape their environments? They're huge, big, exciting questions that we're now not just able to ask, but maybe even able to answer in the next few years. And so the James Webb Space Telescope, I think, is one of the major observatories that will do this, but there are other observatories coming online that will really add to this picture. And so I think it's a tremendously exciting time. And I hope that you'll follow, if you have a passion for this, you can follow that passion and really be some of the people who can help push us into this next era where we really understand our universe in a very deep way. And I think that will be tremendously exciting. So I'm very hopeful for the future here.
Thank you. Thank you, Mike. Thank you for joining us. And now we can possibly finish our interview, the webinar. And I'd like to express our deep gratitude for your time, Mike. Thank you. Bye-bye.
Thank you very much. I really appreciate it. It was very nice to sort of meet you all.
Thank you.
Bye.